So what are the challenges? Well, they're big. We need to heat a large volume of deuterium and tritium, and I say large volume, this is like several hundred metres cubed, to over 100 million degrees centigrade. We have to demonstrate a high power amplification. That is to say the power out has to be greater than the power in, otherwise it's not wholly useful for power generation. We have to demonstrate an extended burn. Okay, this hasn't been demonstrated yet. It has worked. JET actually produced 16 megawatts of energy output, megawatts is power, of power output, but not as electricity, just as neutrons flying out of the thing. So from that point of view, it works. We need to demonstrate technologies that are essential to the reactor in an integrated system, and those, the real difficult ones are the high heat flux components of the first wall and of the blanket. And that is a material science exercise, and that is one of the big question marks. Although that question mark is getting smaller as the research continues, in that materials are being generated that will actually handle not only the heat load, but the neutron flux. A lot of neutrons going through a material displaces the atoms in the material, and so whatever you make has to be able to withstand many displacements of the atoms within its structure. And lastly, we need to ensure the reliability of a very complex system. So this is exactly what ITER is designed to do. This is ITER here, the International Tokamak Experimental Reactor. And that is the next big experiment. Everything is converging. However, the fusion work really is done on modelling because we don't have a reactor to use to actually give us the information. However, all of the studies, which are a few major studies in the States, also in Europe, indicate that even if you take ITER as it is built and build something which can work marginally better, then the cost of the electricity coming out will be comparable to what we have to pay at the moment for most types of electricity. However, the proviso on that is if it works reliably. That is it. So in 50 years' time, we'll see how we go. Thank you.
Thanks very much, Andrew. I, for one, would like to be around to see that because it all sounds rather amazing. Dr. Tony Vassallo, who is our third speaker and the second respondent this evening, is Director of Invenergy. I was rehearsed on how to say that. Invenergy, a company that he has set up in 2003 to provide consulting services in the field of sustainable energy, particularly in promoting the introduction and acceptance of new energy technologies. Tony is also Executive Director of Zest Energy, a company involved in providing advanced regenerative fuel cell systems for electricity storage. Prior to his work in these two companies, Tony spent 23 years with CSIRO, the CSIRO, latterly as the Senior Principal Research Scientist in the Division of Energy Technology. In this position, he set up and was the inaugural Director of the Centre for Distributed Energy and Power, a consortium. He instigated and installed the first microturbine in Australia at the CSIRO Ryde Laboratory in 2001, and was previously Business Development Manager for Energy Storage and Project Leader of the Supercapacitor development at CSIRO Energy Technology. Tony's CV has a strong, two strong themes, which I think are worth particularly mentioning as a precursor. One is clearly a very strong scientific background, and the second is the application of those scientific technologies. And I think it's terrific that he's here this evening to actually now look at some of the implications for what we've heard in terms of the viability and commercial application. Thank you, Tony.
The proposal really that I'm going to put to you, I'll give you my conclusions first, and then you can see how I've arrived at them by the time I get to the end. Firstly, urgent deep cuts are going to need to be undertaken very quickly, and there's going to have little time for new technology development. Fossil fuel-based electricity costs are going to rise, I suspect much faster than people expect, and they're going to meet a downward cost curve from renewables, which I'll be able to demonstrate a little bit into the talk. In Australia, I don't think nuclear is going to make a significant contribution. That's not to say that internationally it's not, but I don't think in Australia we will see an operating nuclear power station for a long time. However, we'll see. Clean coal is going to struggle to demonstrate timely and economic effectiveness, but we may end up seeing some carbon capture and sequestration for coal combustion. Solar, wind, geothermal are going to become increasingly attractive as fuel prices rise and fuel supply security deteriorates. I may not have time to go into that in too much detail. And I guess an outcome of that is the decentralised supply being gas, small gas power stations, solar power stations, biogas, are going to become urban integrated. They are going to move back into where people live and use electricity. And there are very good reasons as to why that will become the case. PV and solar thermal will grow strongly. And because I haven't got much time today, I'm going to focus most of my attention, I guess, on the nuclear issue and the PV technology. There is a lot of emotive pull and push in the media these days. The science is actually suggesting that, in fact, things are happening faster than was first thought. And a lot of the images that we see now, which may not be directly related to climate change, may be more related to weather, but these images are starting to make people think, well, what is the timescale that these changes might occur? And generally, the accepted position is that a dangerous climate change can be avoided if you remain below 2 degrees above pre-industrial levels. So I think what we're going to see as a community, that over the next couple of years, there's going to be an increasing urgency felt by the community in general, by events that are happening, and I think that will drive the political process to push things to happen a bit faster. And some of the timescales that we've heard about really just don't fit into that. Traditionally, people have looked at the options of generating electricity and think centralised, coal power stations, nuclear power stations. These are large power stations remote from where people use electricity, generally on the coal fields, nearby, near with plenty of water. The other option being nuclear, also a centralised option. And you can understand where these have come from. This is how the engineers have grown up. The politicians have evolved into this mindset that centralised large-scale power generation is the only option. It's the only game in town. Now, I want to try and show you that, in fact, that's not necessarily the case, given that we have a national government and state governments that are not looking at, going down the nuclear line. So even if you had an electoral cycle, you could see that nuclear is not going to make a big difference in Australia for 20 years plus. And I think that by the time we work through that period, the community's not going to be sitting back saying, yes, well, we'll wait for nuclear, when the pressure on governments from society, communities, is showing that we have to act a bit faster. Has been under construction since May 2005. The plant has fallen 2 years behind and at least $1 billion over budget. Very, very hard to build a nuclear power station quickly and cheaply. Costs are going up hugely. I understand there's only 1 or 2 companies in the world that can actually provide the forgings for the containment vessels. One in France, one in Japan, I think. And if you think you can go in and order a power station now and see anything within 10 or 12 years, then I think you're very optimistic. So the time delay in terms of getting an operating power station and getting the capital to finance that, I think, would really slow it down.